Thank you. Thank you for joining us today to talk about the James Webb Space Telescope, particularly on the eve of its impending and much anticipated launch. Dr. Greenhouse has served on the James Webb Space Telescope senior staff since 1997. He specializes in infrared spectroscopy, development of related instrumentation and technologies, flight project science, and technical development, technical management. Having graduated from the University of Arizona with a bachelor's degree in geosciences, Matt Greenhouse received his PhD in physics from the University of Wyoming in 1989. Thereafter, he joined the Smithsonian Institution, where he played key roles in several NASA and European Space Agency science missions. Several years later, he moved to NASA's Goddard Space Flight Center, where he assumed responsibility for the science instrumentation on the James Webb Space Telescope. Dr. Greenhouse is the author of more than 100 scientific publications. With that, again, Matt Greenhouse, welcome to the Greenway Talk.
It's my pleasure to be here. And thank you all for tuning in. I'm going to go ahead and share my screen.
Okay. And I'll ask everybody to turn off their microphone.
Wait a minute.
As we'll take questions at the end.
Stand by. I didn't quite do that right. Stand by one moment. I have to share sound. There we go. Okay, does everyone see a chart on their screen? Is that a yes?
That's a yes.
Okay. Well, thank you all for tuning in to hear about the James Webb Space Telescope. Now, space telescopes are our most powerful tool for looking back in time. Excuse me. Traveling back in time is the stuff of science fiction, but looking back in time is something that we can actually do. And telescopes are the main tool for doing that. So how does it work? Light travels at a finite speed. And so there is a transmission delay associated with that. So if you were to look at someone seated in the room with you right now, you're not actually seeing them as they are. You're seeing them as they were a few nanoseconds ago, because that's how long it takes light to travel from that person to your eyes. Now, a nanosecond is a really, really small amount of time, a billionth of a second. So that transmission delay is imperceptible to us. But if we look at objects that are farther away, the delay becomes much bigger. For example, if we had a magic switch that could turn off the sun, and we flip that switch, it would be 500 seconds before we saw anything happen. That's because it takes 500 seconds for light to travel from the sun to the earth. So when we look at the sun, we're not seeing it as it is, we're seeing it as it was 500 seconds ago. And so it goes. When we look at the closest star, we're seeing it as it was 4 years ago. And we look at the center of our galaxy, we see it as it was 25,000 years ago, and so forth. And so with telescopes in space, we can look back in time to study the formation and evolution of the universe. And depending on what we're trying to study, we need various kinds of telescopes in space to do that. Now, the JWST mission was conceived in the mid-1990s as a mission to connect the dots, if you will, between this famous image taken by NASA's COBE satellite of the oldest light in the universe, the moment in the evolution of the universe when the universe became transparent and light from the Big Bang could escape. It's about when the universe is 300,000 years old or so. And this map of this light, here the colors encode temperature, and these small temperature inhomogeneities that are seen in this image are the seeds that will eventually form into stars and galaxies. Now, at about the same time, the Hubble Space Telescope was flying, and it took the deepest image that it was capable of taking at that time. So it looked as far back in time as the Hubble can see to produce a famous image called the Hubble Deep Field. And that image shows us what the universe was like when it was about 1 billion years old. And in this cartoon of the evolution of the universe, the zone, the epoch in time between the epoch that Kobe observed and what the Hubble Deep Field can observe is a mysterious epoch known as the cosmic dark zone. And it's of great scientific interest because this is the period in the evolution of the universe when the first stars and galaxies formed. It's been poorly studied because we haven't had the right kind of telescope in space to study that epoch. And that was the major initial impetus for the JWST mission. Now, when Hubble took that deep field image, it did so by staring at a single spot in the sky for a long time, about 2 weeks, leaving the camera shutter open, if you will, and to take the deepest image that it could take, to look as far back in time as it could. And this is what one sees in that image. And there's a lot of nearby faint galaxies in this image, but there are also these very faint red objects, which are highly redshifted primeval galaxies that are further back in time than Hubble can see. So with Hubble, we can't look back all the way to the beginning of stars and galaxies. But with the JWST, we will repeat this experiment, stare at a spot in the sky for a long time, and it will go much the way that the Hubble observation went. But with JWST, we can see farther back in time. So we should literally see back to the galaxy formation epoch. So there will be nothing left to see in those deep field images beyond what JWST can see. And we'll talk about what some of those special features of JWST are that allow us to do this. Now, when we say that the JWST will see the first galaxies, we don't mean that you will pick up a copy of the newspaper and see a picture of the first galaxy. What we mean is that JWST will measure the star formation rate per unit volume in the universe as a function of look back time or redshift. This is to find the formation epoch. This is what we know today. And you can see that as we go to high redshift, as we look way back in time, the data stops because we haven't had JWST. And you can also see that the error bars in the data become very big. So JWST will fill in this area and in such a way that we will not only see the epoch of the first galaxies, but we will be able to discriminate between various theoretical models of how the universe evolved. So it should be a very exciting time for cosmology. It may very well revolutionize what we understand today about the evolution of the universe. Now, we can model the evolution of the universe with supercomputers, and this is a supercomputer simulation of the evolution of the universe. And you can see that most of the normal matter in the universe is distributed in a spider web type arrangement called the cosmic web. And JWST will be able to help us understand how this web-like structure, formed after the Big Bang. And it should give us our first look at the formation of the cosmic web. Now, when we look at galaxies nearby that Hubble can see, the galaxies are very symmetric. They have very regular morphologies or symmetric shapes. Some have spiral arms, some have bulges, but they're very, very symmetric objects. When we use the Hubble to look back in time as far as it can see, the most distant galaxies that Hubble can see do not look like the nearby galaxies. Their morphologies are very irregular. And so one thing that the JWST will help us do is understand how the morphology of galaxies evolved from the very primeval ones here when the universe was 1 billion years old at a redshift of 6 versus the more nearby galaxies. We still don't understand that, and the JWST will help us observe that process. Now, with Hubble and looking at relatively nearby galaxies, we do see a lot of irregular galaxies shown here in Hubble imagery. And we can model how those galaxies form as collisions resulting from collisions between galaxies. What you see here is a supercomputer simulation of 2 galaxies colliding. And with simulations like this, we can actually reproduce those irregular morphologies that we see. And so we suspect that in the early universe, collisions between galaxies were more common than they are today, but Hubble will help us understand that. Now, you've all heard the statement that space is expanding or the universe is expanding. What do we mean by that? Here in this cartoon, you have a loaf of raisin bread dough that's been set out on a counter to rise. Now imagine that you were sitting on one of the raisins. What would you see? You would see all the raisins moving away from you, even though you are not at the center of the expansion. And no matter what raisin you chose to sit on, you would see exactly the same thing. So this analogy is a pretty good analogy for the actual situation that we have in the universe. Here, the raisin bread dough itself is expanding. The raisins are not flying through the dough. And when we say space is expanding, we literally mean that space, the space between the stars, is expanding. We don't mean that the stars are flying through space, like resulting from an explosion. So what does all this have to do with JWST? Well, the light from those primeval galaxies, those first galaxies, is emitted in the ultraviolet part of the spectrum. But as that light travels through the expanding space to us, as the light travels through that expanding raisin bread dough, its wavelength is stretched from the ultraviolet into the infrared. So in order to see those primeval galaxies today, we have to build an infrared telescope. Now, the infrared capability that we put into the JWST is useful for lots of other science, but it's absolutely critical for seeing the first galaxy. So that was a driving requirement on the JWST. So what do we mean by the infrared? Light exists in an infinite spectrum of wavelengths, from very, very short to very, very long. And the light that our eyes can see, our eyes are only sensitive to a tiny slice of this spectrum. It's the wavelength of light that can penetrate the atmosphere and reach the surface. Our eyes have evolved to be sensitive just to that waveband. Now, shortward of the light we can see, if we make the wavelength a little shorter than our eyes can detect, then we're in the ultraviolet part of the spectrum. Our eyes can't see it, but your skin can be burned by the ultraviolet light if you stay at the beach too long. The Hubble Space Telescope is designed to observe primarily the visible and in the ultraviolet part of the spectrum. You can see a little bit of the near infrared. The James Webb Space Telescope, in contrast to Hubble, is designed to observe from the red edge of the visible out into the mid-infrared. If we make the wavelength of light a little bit longer than our eyes can see, that is the infrared part of the spectrum. And although our eyes can't see it, your skin can sense it. So if you hold your hand near an electric stove burner, for example, that is not turned up so high that it turns red, but if the burner is black, you hold your hand near it, or a radiator, you'll feel the heat. And what your skin is feeling is the infrared light being emitted by that burner. So the JWST is designed to operate in the infrared part of the spectrum. Our eyes can't see that light, but our skin can feel it, and it's very important for the science investigations that we're going to carry out with the Webb. Now, the spaces between the stars in our galaxy and others, the so-called interstellar space, it's not an empty, cold vacuum. That space is filled with giant clouds of molecular gas and dust. It has plasma and atoms. There's a lot of stuff in this space. And if we look at this large image here is the Eagle Nebula. So this is a giant molecular cloud that's had some newly formed stars in it. And those stars have ionized the gas around them, causing this visible nebulosity. And if we zoom in on a part of that, as Hubble did, and to produce this very famous image that Hubble took of the Eagle Nebula. And these big pillars that you see here are pillars of a giant molecular cloud, and they're opaque because there is dust mixed in with that molecular gas. However, this is a visible light image taken by Hubble. If we observe that same field in the infrared, the longer wavelength infrared light can penetrate the dust, enable us to see star formation that's occurring inside the molecular cloud. And this is an example of how the infrared capability that we put into the JWST to see the first galaxies is useful for lots and lots of other science, in this case, understanding how stars form. Now, we know the basics of how stars form. We have these giant molecular clouds in space, and those clouds begin to collapse onto themselves by self-gravity. And when that happens, the pressure inside the cloud begins to climb. It begins to get warm. The situation is very similar to filling your bicycle tire at the gas station. When you inflate the bicycle tire, it gets a little bit warm. The same thing happens inside on the cores of these molecular clouds, only in this case, it gets really, really, really warm to the point where nuclear fusion can occur. And then then the star is born at that point. And when stars are formed, there is typically a disk of debris surrounding the newly formed stars. And these circumstellar disks are of tremendous scientific interest because they are the birthplaces of planetary systems like our own. Now, so JWST will be studying circumstellar disks a lot. Now, when planets form in these disks, the planets sweep up the disk material to sculpt the disk, as shown here. And this is a computer simulation of that process. And so here there are planets in this circumstellar disk, and you can see that they are sculpting the disk by sweeping up the material. So we can detect the fact that there are planets in this case without even being able to see the planets. In the upper right here, this is actual imagery taken by a giant radio telescope in Chile, showing actual images of this process. And JWST will do a lot of this work in an effort to help us understand how solar systems form. Now, in the upper left here, we have an artist's rendition of the debris disk surrounding our own star, the sun, alongside a map of where that debris actually exists. This debris, these chunks of rock and ice, are of tremendous scientific interest because this is primordial material, pristine primordial material that is left over from the formation of our solar system. So we want to study that in an effort to really understand the processes by which our solar system formed. So these objects are called the Kuiper belt objects or trans-Newtonian objects. We can observe them from the Earth, so we know where they are, but they're very poorly studied. Recently, we visited a Kuiper belt object for the very first time in 2014 on NASA's New Horizons mission that was sent to fly by Pluto. After it finished the Pluto part of the mission, we sent it on to this Kuiper belt object to take this first image of a Kuiper belt object. And this is what we saw. It was two objects that were stuck together. And this has been modeled as resulting from a low velocity collision, just a few kilometers per second, show that these particles, these bodies can stick to each other without either one being destroyed by the interaction. And this is of great interest to understanding how planets form, particularly models of planet formation that work by agglomeration of small particles into successively larger bodies over 100 million years or so. So this will be an important area for JWST. And we've had to put special tracking, special non-sidereal tracking into the JWST to enable it to observe those Kuiper belt objects and also the outer planets of our own solar system. The JWST can observe the outer planets and Mars. And with Webb, we will be studying the planets of our own solar system. We will study Jupiter. We'll be studying the Great Red Spot of Jupiter. This is a storm that's been raging on Jupiter for more than 400 years. And today we see that that red spot is shrinking, and we still don't understand why it's red. And JWST will help us work on those problems. The Webb will also search for small moons of Saturn that were too faint for flyby spacecraft to have observed. Now, liquid water in the solar system is not limited to Earth. In fact, it's possible that most of the water in the solar system is outside the Earth. JWST will study moons of Jupiter and Saturn, particularly Europa and Enceladus. And because those moons are known to have vast oceans that are enclosed by a giant crust of ice. And as tidal forces act on those moons, the ice necessarily cracks and geysers are observed erupting through the ice. Here in the lower right, this is an actual image from the Cassini spacecraft, an image of Enceladus showing this ejecta through the ice. JWST will study that ejecta a lot to understand its chemistry. We're pretty certain that that's water. In fact, Hubble has recently, observed water on the vapor emanating from the trailing side of Europa. And JWST will do a lot of spectroscopy on this ejecta to help us understand it. It is possible that life could exist in these oceans independent of the sun, as we see it exist independent of the sun on the mid-Atlantic ridge in our own planet. Now, when I was a graduate student, there were no planets known outside our solar system. Today, we know that basically all stars have planets, with the implication that there are billions of habitable worlds in our galaxy. We don't know that they're inhabited, but we have learned how to search for life on them by studying their atmospheres. And so the search for extraterrestrial life is no longer the stuff of science fiction. It is very much a major objective of NASA astrophysics. So how can we search for life in an atmosphere of of an exoplanet, as the term is. Planets that orbit other stars other than the sun are called exoplanets. They're very far away, of course. So how can we search for life on them? We use something called a technique called spectroscopy, in which we can spread light out into its component colors with optics so that we can observe emission of light by individual atoms and molecules. And we have learned how to do that over quite a long time with great precision, such that we can not only see the light from the atoms and molecules, we can actually identify which atom and molecule is producing the light. So a spectrum is simply a plot of brightness versus wavelength. And here we show a spectrum of the Mars, Earth, and Venus. And so imagine brightness on the y-axis, wavelength on the x-axis, and all these bumps and wiggles are emission and absorption of light by individual atoms and molecules in the atmosphere of the Earth. If the Earth had no atmosphere, this would be a flat line. So by doing spectroscopy of exoplanet atmospheres, we can measure their chemistry. And by measuring their chemistry, we could look for chemical species that would not be expected absent biological processes. We look for chemistry that is way out of equilibrium for a system that does not have life. For example, the Earth would not have nearly as much oxygen in its atmosphere if we didn't have life on the Earth. So how do we do this spectroscopy? The most powerful technique that Webb will use is called transit spectroscopy. And it works like this. Imagine that we have a star and we have a telescope with a spectrograph. And imagine that along our line of sight between our telescope and the star, we have a planet orbiting the star. And the planet gets in our line of sight to the star. We take a spectrum. What do we see? We're going to get a spectrum of the star plus the spectrum of the planet's atmosphere. Now we just wait a little while for the planet to move out of the way in its orbit, and we repeat the measurement. Now the planet's not there, so we just get a spectrum of the star. We subtract the two, and voila, we have a spectrum of the planet's atmosphere. And this has been turned into an exact science by Hubble and other facilities. And JWST will do a great deal of transit spectroscopy on exoplanet atmospheres. JWST can detect water on an exoplanet that is just a few times the size of the Earth. Why do we care about water on exoplanets? It's not because alien life might get thirsty and need something to drink, but rather for the organic chemistry of life to occur on a planetary scale, one needs to have a liquid solvent available on a planetary scale, and water is what we're most familiar with. Now, when we first put pencil to paper on what type of telescope we had to build to do all that science, we realized that we needed 7 times the light gathering capacity of the Hubble Space Telescope. And we also needed Hubble's ability to see fine detail, angular resolution, they call it, but at a much longer wavelength than Hubble. And as it turns out, that also requires a mirror bigger than Hubble. And we needed to endow the JWST with an observing capability that spans the optical to mid-infrared spectrum for the reasons that we discussed. To see those first galaxies, we need to be in the infrared. Now, when we realized these 3 things, we then realized that we had 2 huge problems that almost stopped the whole project dead in its tracks. To build a mirror that has 7 times the light gathering capacity of the Hubble Space Telescope, that mirror turns out to have a diameter that is larger than the biggest rocket that was available to us. So that was problem number 1. And then problem number 2, to build an infrared telescope, the telescope has to be made very cold. And this is because anything above absolute zero emits light. So if you were to put infrared goggles on and look around the room you're sitting in right now, you would see your body glowing in the infrared. The walls and floor of the room would be glowing in the infrared. If we didn't make the JWST very, very cold, it would be blinded by its own infrared emission. How cold do we have to make it to prevent that? Turns out we have to make it really, really cold, almost minus 400 degrees Fahrenheit. And there was no mechanical refrigerator then or now powerful enough to cool the JWST to such a low temperature. So let's take a look at how we did solve those problems, obviously. So let's take a look at how we did it. Let's talk about that thermal problem first. We're not going to put the JWST in orbit about the Earth the way the Hubble Space Telescope is. We're going to put it in a special spot in space called the second Lagrange point of the Sun-Earth system. That's a mouthful. We just call it the L2 point for short. And that point is about 1 million miles from the Earth in the anti-sun direction. Now, why do we want to put the JWST there? The reason is that, as you can see from this diagram, when the JWST is at the L2 point, and realize that as the Earth orbits the sun, this pattern of L2 points orbits with it. And so all the sources of heat on the JWST, the sun, the Earth, and the moon, will always be in the same direction if we put the JWST here at the L2 point. And so then we realized that if we deployed a giant sunshield that would allow the JWST to live in its shadow, then the JWST will cool passively to the cold darkness of space without a mechanical refrigerator. But the JWST has to be able to point all over the sky to be useful as a telescope. So we had to design this sunshade to enable that. We sized the sunshade so that we could tilt the JWST 5 degrees toward the sun, we're still in the shadow, and 45 degrees away from the sun, and we're still in the shadow. So we've observed an arc on the sky 50 degrees long without getting out of the shadow. Now, if you look at this diagram, you can see intuitively that if we rotate the JWST about the Earth-Sun line, about this axis, that doesn't spoil our shadow situation at all. So now this arc is turned into an annulus that covers 35% of the sky. So at any instant in time, JWST can observe 35% of the sky and still be in the shadow of its sunshade. Now, as the Earth orbits the sun, now we're rotating about this axis. And one can see that this annulus will sweep over the whole sky every 6 months as the Earth moves in its orbit. And so every 6 months, JWST can observe any spot on the sky without getting out of its shadow. So that's basically how we solve the cooling problem. Now, we don't put JWST exactly at the L2 point. Why not? Well, we're generating electricity on JWST with solar arrays. It takes about 2 kilowatts of power to run the Webb. And so it's important that the JWST stay outside of the Earth's shadow. And so we're putting it in an orbit about the L2 point. It's called a libration point orbit. And that orbit is unstable in the direction of the Earth-Sun line. And so that orbit has to be maintained with station-keeping thrusters. The propellant for the station-keeping thrusters is sized to last about 10 years. It could last quite a bit longer, depending on how efficient we are at operating the JWST. But that propellant is what will ultimately limit the duration of the JWST mission. When that propellant is finally exhausted, the JWST will fall out of this orbit into a generalized sun-centered orbit, and the mission will be over. And so this is how it works. The JWST, as you can see here, is orbiting the L2 point as the Earth is orbiting the sun. And this allows us to cool the JWST and still point it all over the sky. All right, how did we deal with that big mirror? We adopted something called a segmented mirror architecture. And so rather than build a single big mirror the way we normally do when we build telescopes, we made 18 hexagonal segments and mechanized them so that they could play together as if they were a single mirror. And this segmented architecture then allows us to fold the mirror inside of the 5-meter diameter fairing of the Ariane 5 rocket that we're using to launch the JWST. The Ariane 5 will be launched from Kourou Launch Center in French Guiana, which is on the east coast of South America. JWST is at the launch center now. JW will fly directly to the L2 point. It doesn't orbit the Earth even once. So it's on something called a direct transfer trajectory. JWST is about 6.5 metric tons. And in the next slide, we'll show how it unfolds from this configuration into a working telescope. In that origami, if you will, involves 40 deployable structures and 178 release mechanisms, all of which have to work perfectly. Unlike Hubble, the astronauts cannot go to the Sun-Earth L2 point. So if we don't get this deployment right, the astronauts cannot go out there and fix the JWST. So we've had to do lots and lots of testing to ensure that we know what we're doing. When the JWST comes out of the fairing, the first thing that happens is the solar array comes out so we can become power positive. We're operating on batteries up to this point. There are some rocket firings. And now the high gain antenna deploys so we can begin communicating with the JWST. There are some rocket firings that get us on trajectory to the L2 point. And what you see unfolding here are pallet structures that contain that giant tennis court sized Sunshield. Here you see a telescoping boom come out to provide thermal separation between what will be a real cold telescope and what must remain a room temperature spacecraft. And now you see these mid-telescopic booms deploy that are pulling the sunshade out of those pallet structures. The sunshade is carefully folded in there, and it gets pulled out, and these spreader bars on the periphery spread it into its 5 layers that give it the thermal performance we need. A trim tab comes out to help us trim the solar sail, and a few other radiators deploy that help us cool specific pieces of equipment on the vehicle. And now you'll soon see the secondary mirror of the telescope deploy. And then the wings of the primary mirror will deploy much like a round drop leaf kitchen table. And there you have it. All right, now the JWST mirrors are not made of glass like the Palomar mirror and most telescope mirrors. And they're made of a material called beryllium. Why did we use beryllium? As the telescope slews across the sky, even though it's in its shadow of its sunshield, there will be small thermal gradients that will form in the mirror as we point in various directions around the sky. And we don't want those thermal gradients to spoil the shape of the mirror. And so we've had to find a material that had a low coefficient of thermal expansion at the operating temperature of about 50 Kelvin. And it turns out that beryllium has that property. And beryllium also has high thermal conductivity, which suppresses the gradients, and it has a high stiffness to mass ratio, which is very important. When building something that flies, whether it's an aircraft or a spacecraft, weight is really, really a premium. So the beryllium starts out in a powder form, and then we have to compress it under tremendous heat and pressure to form a block of material called a billet. And then after we go through all the trouble to do that, we machine away almost all the beryllium. This is the backside of a mirror segment, in order to make that mirror segment as light as it can possibly be. The figure of merit here is called areal density, mass per unit area. And by that metric, the JWST mirror segments are about 6 times lighter than the Hubble mirror. And these represent the current state of the art for lightweight flight telescope mirror segments. All right, now if you're paying attention, I know some people in this audience know a lot about telescopes and maybe even making their own telescope. You'll realize that we have another big problem. How do we polish mirrors? We polish mirrors by rubbing on them with gritty stuff until they get smooth and shiny enough. Well, that's a room temperature operation. And so if we're going to polish the JWST mirrors at room temperature and then use those mirrors at nearly minus 370 Fahrenheit, that means that we have to polish in the wrong shape at room temperature in order to get the right shape at the operating temperature. This is done through the magic of computer modeling, but computer modeling is not perfect. And so we had to follow an iterative process in which we would polish the JWST mirrors partway and then put them into a specially instrumented space simulation chamber at Marshall Space Flight Center in Huntsville, Alabama, which is designed to simulate the operating environment that these mirrors will see, the vacuum and cold environments that is produced by this large vacuum chamber that is lined with shrouds that are cooled by liquid nitrogen and liquid helium. And we could put the mirrors into that chamber and observe them with special optics test equipment to compare our model to reality. Then we would make corrections to the model and go back to the polishing house and do that iteratively until we could get the result shown in the upper right here. This is real data. So this is what the figure of a JWST mirror segment, this particular one, looks like at ambient. Here the colors are encoding relief. And when we cool it down, we just get this beautiful flat surface. And so this was a lot of work. It took many years. It's all behind us now, and it was done successfully. Now, it's not enough just to build mirrors. We have to build a structure that can hold those mirrors. And the requirements on this, the structure of this telescope they're very, very daunting requirements. It has to be a light structure. It has to be a strong enough structure to hold all the optics in exactly the right place to within a fraction of wavelength of light. And at the same time, it has to be strong enough to withstand the tremendous inertial loads that this telescope will experience when it's launched in the rocket to space. And then it also has to withstand about 300 degrees of temperature change. And so these were very daunting requirements. We had to invent a composite material that could meet these requirements. And this is what the telescope structure actually looks like before it's populated with optics and all the other equipment. The structure involves more than 3,000 parts that have to be precision bonded together. And so this was a major engineering achievement, and it's all behind us now. Now, what you see here is a robotic pick and place machine. This is in a clean room at Goddard Space Flight Center. And what's happening here is this machine was designed and built to help us install those 18 mirror segments onto the backplane structure. These are the actual flight mirrors. They look black because they have covers on them to keep them clean. And this robotic arm has a very high precision end effector on it that's helping the technicians get these mirror segments in exactly the right position. You get the idea. All right, now those mirror segments have to play together as if they were a single mirror. And so we've had to design mechanisms that we can put on the back of the mirror, that we can move the mirror in 7 degrees of freedom to within a fraction of the wavelength of light. And that's not an easy thing to do, but we did do that. And so each of these mirrors are mechanized. And when we get the JWST in space and we look at a star for the first time, what we have is 18 separate telescopes. And we have to then go through a process of wavefront sensing and control to superpose the imagery from each of those 18 segments into a single nearly perfect image. So the JWST will produce an image which is within 80% of a theoretical perfect image. This will take place during the first month of flight or so. All right, that Sunshield is one of the tougher parts of the JWST. It's one of the higher risk areas in the mission and one of the most difficult aspects to build. It is literally the size of a tennis court. It's 73 by 40 feet. It's made of a heat-resistant plastic material called Kapton. The sunward facing side is coated with silicon, so it actually looks pink in reality. And the remaining surfaces of all the other layers are coated with aluminum to give it the thermal properties that we need. This sunshade has an SPF of 1 million. If you had it on the beach, you would be very well protected. And it takes 5 layers to get that SPF of 1 million. And it also takes a special curved shape. Now, those of you who sew may realize that to create a curved shape out of flat cloth, you have to have lots of seams. And so each one of these layers is itself a quilt of 50 pieces. There's 7,000 inches of seaming involved in putting that quilt together. In this case, it's not done with needle and thread, but with thermal spot welds. And so there's just lots and lots of complexity in building this Sunshield, but it's been very rigorously tested, and it's in great shape to launch in about 60 days. All right, this is just an example of a test that's geared toward really understanding how to fold this Sunshield into this pallet structure. These plastic tables are there to provide gravity offloading. So those are not there in space. And you can see those mid-telescopic booms that you saw in the animation here are pulling the sunshade out of the pallet structure. You'll notice a person in the middle here that gives you a good sense of scale, you know, how big this thing really is. You can see the quilting if you look carefully. And here you'll see how those spreader bars are separating the 5 layers. So just an example of some of the kind of testing that we need to do to understand how to build things like this. Engineering is very much an empirical science. So testing is at the core of everything we do. Now, in the system, the job that the telescope does is to collect the light from the objects of interest and relay that light or focus that light into the science instrument payload, which in the case of this observatory resides on the back of the primary mirror. And these science instruments do a little processing on the light and then digitize the light into 1s and 0s so that we can transmit the data back to Earth by radio transmission. And so extracting the physics information from that starlight is what modern astronomers do. And that's what these science instruments are designed to enable that extraction to occur. So let's take a look at those instruments. This is the near-infrared camera, the main near-infrared camera on JWST. We call it the NIRCam. And this is the instrument that will observe those primeval galaxies and take much of the imagery that JWST will take. This was led by the University of Arizona and built by Lockheed Martin Advanced Technology Center in Palo Alto, California. This is here in the upper right is the main near-infrared spectrometer on the JWST. This is a very unique spectrometer in that it is a multi-object spectrometer. This is a spectrometer that can obtain spectra of 100 different objects simultaneously and keep those spectra separate. We had to invent that capability for JWST because those primeval galaxies that we want to observe in that cosmic dart zone that we spoke of, they're really, really, really faint. So one has to keep the camera shutter open, if you will, or integrate for a very, very long time to see them. And if we tried to observe them one at a time, we would never get a large enough sample size to do the science that we need to do. So we had to develop this multi-object capability. This instrument was produced by the European Space Center in Noordwijk, Holland, in partnership with Goddard Space Flight Center. This is the mid-infrared instrument on the JWST. This observes the longest wavelengths that JWST can see. It's both a camera and a spectrometer. And this instrument has to operate even colder than the JWST. And so it is mounted on these carbon fiber thermally isolating struts, and there is a small cryocooler, a mechanical cryocooler, that cools this instrument all the way to about 6 degrees above absolute zero. This instrument will give humanity its first high-definition view of the infrared universe. For the very first time, we will be able to see the infrared universe with the same clarity as Hubble shows us the optical and UV universe. Then finally, we have the Canadian instrument. It is a fine guidance sensor that is used to point the JWST. It can sense pointing to about 1/millionth of a degree or 3 milliarc seconds. And it also has a science function that is very much geared toward doing that spectroscopy of exoplanet atmospheres. And so these are the instruments that we're carrying to space on the JWST, and they should revolutionize our understanding of astronomy in much the same way that Hubble did. Now, after we got that instrument package integrated with the telescope and got the whole telescope assembled and squared away at Goddard, we had to put it into a special shipping container, a truck-mounted shipping container that preserves the JWST in the special ultra-clean environment that it requires. And then we designed that so that it could fit inside a C5 transport plane. It just barely fits in there, as you can see, but we did get it in there. And we flew it from Andrews Air Force Base to Houston, Texas, in order to do more testing at the Johnson Space Flight Center near Houston, Texas. And here we chose to do something called an end-to-end optical test. Now, the mental image that you get when I say end-to-end optical test is exactly the right image. This is a test in which we're going to put the entire observatory into a space simulation chamber, cool it, down to its operating environment as best as we can simulate it, and observe special optics test equipment in the top of this giant chamber to shine light through the telescope in the whole system the way it will occur in space to make sure it works. Now, this is a test that we did not do on the Hubble Space Telescope program, with consequences that many of you are aware of. So we elected not to skip that test on the JWST, but it's a very difficult test because the JWST is so enormous. We had to go find a ginormous chamber to do this test. And at Johnson Space Flight Center, we pulled out of mothballs from the Apollo program the largest cryogenic space simulation chamber in the world, called Chamber A. This is a photograph looking through the door of that chamber, and you can see the Apollo command module inside here being tested in that chamber. We refurbished the chamber for JWST. We were able to roll JW into the chamber on rails like this, suspend it from the ceiling on rods, and carry out this test. It's a very good thing we did the test because we did find problems that we were able to fix. So that work is all behind us now. We went back into the C5 and then flew from Houston, Texas to Los Angeles, California, where our contractor Northrop Grumman Aerospace Systems in Redondo Beach, California, would then integrate the spacecraft and Sunshield assembly to the telescope and instrument assembly. So let's take a look at how that, what that process looked like. This is in a clean room in Northrop Grumman. And here they're lifting the observatory with its science instruments. You can see it's in the folded configuration, and they're attaching it to the Sunshield. This is the actual flight stuff. And you really can't see the spacecraft, but the spacecraft is down here. And of course, as we put all this together, we have to, do a lot of testing to make sure that we've done it properly and that everything is actually working. Now, having reached this level of assembly, we're not done yet. We have to take everything you see here on the screen and put it into a vibration chamber. We're going to put it on a giant table and shake the heck out of it to simulate the vibration that JW will experience during the rocket flight. And then we have to put it in an acoustic chamber, blast it with giant loudspeakers to simulate literally the noise, the acoustic energy that will impinge on it during the rocket flight. And then after we do those tests, we have to comprehensively test the JWST to make sure that we really passed the test. All that work is behind us now and was completed successfully. Now that we've attached the Sunshield and spacecraft to the telescope and instruments, that resulting assembly is now too big to fit into the C5. And so instead, we will roll this, we have rolled this shipping container onto a special roll-on, roll-off transport ship. And we shipped out of Seal Beach, California, and traveled through the Panama Canal to French Guiana. It's almost 6,000 miles. It took us 2 weeks to do that. This is the first time that NASA has shipped the flight system by sea. We had great weather. There were no problems. And that journey was completed successfully. This is us shipping out of Seal Beach, California. It's a key moment for JWST because to this point, about 10,000 people all around the world, their work has come to fruition and culmination to get to this point where we've got it all together and we're shipping to the launch site. So that's the shipping container that now contains the whole JWST. This is so we have arrived. This is the JWST having come off the ship and moving into the payload processing facility at Kourou Launch Center. And here we're unpacking the JWST out of the shipping container in a clean room in Kourou to begin the process of integrating it with the rocket. And this work is occurring as we speak.
This is your telescope, an engineering marvel, an exploration powerhouse. Use it to look back in time and explore the first galaxies that formed after the Big Bang. To peer into atmospheres of planets orbiting the stars. It's your eyepiece to the uncharted, unknown, and unimagined. This is the largest, most complex, and challenging space telescope ever constructed. It will change our understanding of the universe and our place in it. The James Webb Space Telescope. Equipped with the largest primary mirror ever to be flown in space, at 6.5 meters, it's more than 6 times the size of the Hubble Space Telescope primary mirror. Webb's 4 cutting-edge infrared instruments and cameras operate at super cold temperatures. Temperatures colder than the surface of Pluto. Getting this cold is done with the help of the largest Sunshield ever flown. A 5-layer, tennis court-sized Sunshield that blocks heat from the sun, Earth, and moon. Webb will be the first telescope to detect light from the most distant galaxies in the universe. These first galaxies formed about 13.5 billion years ago, only 300 or so million years after the Big Bang. Webb carries advanced technologies to tackle some of the most fundamental questions about the universe. How did the first galaxies form and evolve? Are there chemical signatures of the building blocks of life on other worlds? Is our solar system unique? Launching such a large telescope into space is an incredible engineering challenge. Fully deployed, Webb is too large to fit inside any rocket fairing. Engineers designed it to be folded, like origami, to squeeze inside the European Space Agency's 5-meter diameter Ariane 5 rocket fairing. After launch, controllers on the ground deploy Webb remotely. Deployment is an intricate ballet. For nearly 3 weeks, controllers carefully unfold Webb. After this delicate dance, Webb's golden mirrors are precisely aligned using motors behind each hexagonal mirror segment, adjusting them to form one perfect mirror. Once the instruments are fully cooled, the exploration will begin. Webb is a technological challenge like no other, born of the efforts of thousands of people across the United States, Canada, and Europe. The James Webb Space Telescope is your telescope. Use it to explore, to challenge theories, to see sights yet unseen. It's yours to unfold the beauty and mystery in the universe and our place in it.
All right, well, JWST will really revolutionize, in all likelihood, our understanding of astrophysics in much the same way that Hubble did when its mission began. The general questions that drive NASA astrophysics are: how does the universe work? How did we get here? What is the universe evolving into? What's our cosmic destiny? And are we alone? Webb will help us understand these questions to some extent, but of course it will take many more missions beyond Webb to do that, some of which we're building now and some of which we're planning now. And I don't know if we have young people in the audience this afternoon or not, but if we do, you can join the quest for those answers. imagining a career where you design space telescopes, where you design spacecraft and do missions like this, it's a completely realistic career objective. The people that do this kind of work come from all walks of life in all backgrounds. The teams that do these projects involve every kind of engineering that exists. All kinds of management, even accountants and lawyers are involved in missions like this. And you can join them. There's a quote that I like to read. The book of nature that lies continuously open before our eyes, but it can't be understood without first learning to understand the language and characters in which it is written. It is written in mathematical language and its characters are geometrical figures. That statement is as true today as it was 400 years ago. So to work in this field, to work in aerospace, go to college, study science, engineering, and math, stay in college, and this is something that you can do when you grow up. And if you're in college now, stay there. If you're already studying astronomy, you'll probably use the JWST in the not too distant future. All right, so those are my remarks for this afternoon. You can follow the action of JWST on our website at NASA Web, hashtag JWST and hashtag NASA Web. The JWST will be launching in less than 60 days. And so it's a very, very exciting time for all of astronomy. Now I can stay for about 10 more minutes to take any questions that you might have.
Well, Dr. Greenhouse, thank you very much. The engineering is just, it's overwhelming. But it's a tremendous story. But let's open for questions. Anybody?
Okay,
Go ahead.
I'll ask the first one. In terms of the mission profile, I gather it takes a month to get to the L2 point.
Mm-hmm.
And then you'll unfurl the telescope, get it assembled, and begin a shakedown set and testing. How long will that last, and when should we expect to get discovery data?
Sure. So when JWST launches, most of the deployments that you saw occur very early, because we have to do those before JW gets cold. And so the deployments will happen en route to the L2 point. And then when we get to the L2 point, we have about 6 months to commission the observatory. So this is tuning up the telescope, getting all those mirrors to play together as one, calibrating all the science instruments and so forth. So the science will begin about 6 months after launch. And the science for the first year is already selected and locked and loaded, if you will.
So you will know before the month is out whether or not the deployment was.
Oh, absolutely. Yeah. Yep.
This mission is so full of terrifying moments that the people working on it, you must all have cast iron stomachs there to handle the stress. I mean, I'm thinking that the most terrifying might be the expansion of that Sunshield.
Yeah.
There.
Yep. So we manage, we do very formal risk management in NASA, as you can imagine. And key to that is lots and lots and lots of testing. It's really the testing that drives the cost of systems like this. So we're very confident that the JWST will work as planned. As I mentioned, engineering is an empirical science, and so we've really demonstrated to ourselves that this design, will work, and we're chomping at the bit to get this thing launched.
Matthew, I was just going to ask, when the shield is out, do you have to worry about debris at any point hitting it?
Yeah, the micrometeorites will hit the JWST and the sunshade. And so we had to engineer for that. And so the sunshade is designed to be resilient to micrometeorite impact. When those particles hit it, they only go through one layer. And so we've taken that into account. And that's something that one has to take into account in any spacecraft design.
Other questions? Open up your microphones, please. Other questions? Anybody?
I have a question. I read some time ago about some kind of a shutter system that isolates parts of the image for the JWST. Could you tell us more about that?
Sure. Yeah, that is the magic optic that makes that multi-object spectrometer that I mentioned work. It's an array of microscopic shutters that allow us to block all the light in a field except the light from the objects of interest. So imagine that we had a sheet of metal and we drilled holes in it to exactly match the pattern of stars in some field.
Right.
And then we took the light that would be coming through those holes and relayed it into a spectrometer such that we got a separate spectrum for each hole. Okay, that's basically how the NIRSpec works. However, we couldn't figure out a way to drill holes in a plate of metal for 10 years in space. So we had to invent this technology of that we call microshutters, whereby the sheet of metal is replaced by an array of microscopic trapdoors that can be individually opened and closed under computer control, so that we could create, this opaque screen with holes that match any field that we're looking at. And so that was a big key challenge. And yeah, that's what that is about.
What's the powered phase of the launch and the getting to the L2 point? How do you stop when you get there?
Oh, well, we're going into orbit. Okay, so we're on a direct transfer trajectory to the L2 point, and then we're going to fall into a specific orbit. And so to do this effectively, we do what's called aiming low. We give the JWST just enough delta V to get out there, nothing extra, so that we can easily get into the specific orbit that we want.
Okay. And so the braking at the far end is a minor issue?
What's a minor? Oh, braking. There's no, yeah, braking is not an issue at all. Yeah.
Okay.
What's the mechanism to distribute light to the various scientific packages you have?
It's free space optics, the way it is even on Palomar or a ground-based telescope. The telescope field, each science instrument picks off a piece of the telescope field with a pick-off mirror.
Right.
And then that mirror just relays the light into the instrument.
Mm.
So all the instruments can operate simultaneously, but they observe adjacent fields of the sky.
Mm-hmm.
Well, Dr. Greenhouse, again, thank you very much. And you've been very generous with your time. And I think we probably need to bring this session to an end. I guess all of us, I'm sure, wish good luck to all the members of the JWST team, and good luck on the launch, and we'll all be watching. So
thank you for having me, and have a great rest of your afternoon.
And if I could conclude by mentioning the meeting for 2 weeks from now, next time, the Greenway Talks online will continue, excuse me, on Saturday, November 6th when our guest will be Dr. Chris Lintott, Professor of Astrophysics, Research Fellow, and Citizen Science Lead at the University of Oxford. He will discuss the Zooniverse. He is the creator of the Zooniverse, and he will tell us how more than 2 million Zooniverse volunteers are now creating new ways of contributing to the advance of science. Also, most important, tomorrow, Timothy Thompson, Mount Wilson Observatory trustee, observatory docent, and session director, is continuing his monthly chronicle of the history and achievements of Mount Wilson Observatory. This month's installments of Sundays with Tim begins at 5 p.m. Pacific Daylight Time this coming Sunday afternoon, October 24th. You can join Tim and participate in his presentation by accessing the Zoom login page on the Mount Wilson Observatory website. Thank you again, Tim. Great series. So with that,
Thank you.
my thanks again to Dr. Greenhouse, and my thanks to all of you for being here and supporting the Greenway Talks online. Got a wave. Bye, everybody. And with that, I'll close the meeting, and we'll see you all on November 6th. Thank you very much, guys.
Thanks.
Bye-bye.
Thank you.
Bye.